You gotta emphasize your.
So, So, what was the girl's change in momentum? What was her impulse viewed from the change of momentum perspective? She started at zero, ended at this. So it's one of those cases, which oftentimes happens, but not always. It's one of those cases where your final condition for the momentum really is your change, because you started with nothing. So her change momentum is negative, what is that, 56 roughly? So, but there's another way to look at change momentum. There's another way to look at impulse, in other words, and that's force times time. So that change in momentum, the impulse, is also equal to the way we get impulse, which is force times time. And so that change divided by the time that they give me should be the force. And one of the indicators, clear indicators that I want to take this approach was when they gave me that time. When they give me time and ask for forces, that's almost certainly going to be impulse. Alright, let's revisit the tumultuous, complicated relationship between Shaq and I, shall we? So, here's the deal. All jokes aside, we're gonna need to pay careful attention to this, because how you view the situation makes all the difference in the world when it comes to solving momentum problems. See, this says conservation of momentum. By its definition, when something is conserved, whatever it is initially is the same as whatever it is later. But we would say that that is only true when the forces involved are internal to the system. And here's the thing. You get to choose, depending on what you want to look for and how you want to solve the problem, you get to choose what you consider the system to be. So, for example, if all you did was consider me, just focusing on me, when Shaq pushes me, is that an external or internal force? It's external, right? You're just looking at me, I get pushed by an external force. My momentum is not the same finally as it was initially. Because initially I was at rest, right? And later I have something that's not zero, right? So that would be an external force. The conservation of momentum does not hold. And we would go to impulse. Maybe how long he pushes becomes an impulse. And likewise, if you were to look at just Shaq, even though he does the pushing, the force, the Newton's third law pair force, me pushing on him without even trying. Remember, you don't need, something doesn't need hands to push, right? If I push against the wall, it pushes back. That's why I move this way, accelerate this way. So, once again, force would be external. You would change his momentum. This would not be true. But, if we look at the system as the two of us. So the system consists of these two objects. Is the force internal now? Is it only between the two objects, or three objects, or 10 objects? Yes, the force is what we call internal to the system. Now, wait a second though. Yes. So, Shaq pushes me, right? And we already know that I'll go away with a larger velocity because I have a smaller mass. But let's say when I multiply those two, Wellborn's final momentum, we'll say, is negative 400. And negatives because to the left. Now, Shaq experiences the same force over the same amount of time, experiences the same impulse. So what is his final momentum going to be? Shaq's final is going to be positive 400. Does that mean he's moving the same speed? He's probably moving much slower than me. Because his m times v is m is probably significantly larger. This is where the vector nature of momentum comes in. Because if the forces are internal, this has to be true. Is it? I mean, we're moving now. So how can our momentum be zero? Because it's not like kinetic energy, which isn't a vector. They are vectors. One of them is positive, one's negative. If you add my momentum to Shaq's momentum, you still get zero, right? See, the momentum of a system can be, the total momentum can be zero, even if every part of the system is moving. So, in this case, let's scroll down a little bit. So, initially, we would say the momentum was zero because, well, both of our momenta were zero, right? Afterwards, the momentum is still zero because it's one of ours minus, actually added to the negative, there we go. So, his momentum plus my momentum, which is negative. And we still get zero. Sure. I mean, I'm not generally one to be trusted with firearms. You can probably imagine this. I fell carrying a box of books. A gun? No. So, it's not like I'm against gun ownership. I just think I'm against it for myself. I actually would protest myself getting a gun. I don't think the Second Amendment should apply to me. I think I should be exempt from the Second Amendment, and I should not have the right to bear arms. I mean, I can have bare arms. Which way did the gun shoot?
No. Nope.
No? Okay. So I tried. I did not hear it. Let's leave it alone. So, but theoretically, I've seen enough pictures and stuff and watched enough TV. When somebody fires a shotgun, you have to do it right. You can really hurt yourself. Right? And I'm not just saying by putting like your hand in front of the barrel, like I might do. I mean, like just firing it normally could actually hurt you. Right? Because before you pull the trigger, what is the momentum of the system of bullet and gun? Zero. So after you pull the trigger, were the forces internal? Were they only between the bullet and the gun? Nobody took the gun through it, right? They're just between the bullet and the gun. They're internal to the system. Therefore, the momentum afterwards must also be zero. So the bullet has a certain momentum. Mass times a very large velocity, but a tiny mass, right? The gun has to have the same momentum. Of course, the gun's mass is many times larger, so its velocity is much less. Which one has more, I mentioned this in the last class, but which one has more kinetic energy? Because velocity matters more, right? And you're going to get squared, so mv is the same. They would each start with that, but then if you multiply each of them again by their velocity, their separate velocities, bullet wins, wouldn't it? Yes. All right, so kinetic energies are not the same, but they have to have the same magnitude of momentum, which is why the gun moves backwards. Newton's third law says it has to, right? The same force that pushes the bullet out one end has to push on the gun the other way. Okay? We've done a lot with things where momentum is zero. Let's talk about a situation where you don't always have to have an initial momentum of zero, for example. Here, let's look at this kind of thing from reverse. let's say, we'll get to that question. This is a funny question. Let's say that Shaq and I go out and play some tackle football.
Okay.
This is Shaq, and this is me. All right? So, Shaq's got the ball. I'm going to tackle.
What are your arms? What are your arms, Igor?
So, we'll say that my mass we'll keep it simple. It's a little higher. Okay? Well, let's say he's got to be twice my mass, right?
3 times.
Probably 3 times, but let's go. Let's just keep it simple. All right. Let's say that Shaq has the ball and is lumbering my way with an initial velocity of 1 meter per second.
1 meter per second.
It's not. It's lumbering. It's not lumbering. It's basically walking towards me. Yes. All right. Would you like me to give him 2? I'll give him 2 meters per second. It's fine and insulting to Shaq. I will give him a velocity of 2 meters per second. So, let's say that I am my initial velocity. Oh, by the way, we're going to have to make Shaq's negative. Say he's negative, blah, blah. That's a mess. We'll fix it. Let's say I am moving at 3 meters per second. Positive. I'm just going to erase this and fix it. It's a job. So, what's the initial momentum of the system? If we assume the system is Shaq and I combined, what is the initial momentum of the system? So we would look at the system, find the momenta of each one. So the initial momentum of the system is going to be Wellborn's initial combined with Shaq's initial. And if you look at it carefully, his is going to be negative 400, mine's going to be 300. And so the initial momentum of the system is not 0 in this case. So the overall momentum lies with Shaq, doesn't it? So even though I'm moving faster, I do not have enough momentum. I would have to go even faster to equal his, correct? So when we collide, and I go to wrap Shaq up, my shoulder and my arms reach about here, right? But I would say, basically what's going to happen is Shaq is going to then start carrying, correct? So I run into Shaq. Now, let's do. Which of us experiences the greater impulse? We went down this path earlier.
Either.
Right? Same. Because when I start to hit him, the forces are the same, right?
Yes.
So low, and they occur for the same amount of time. So our changes in momentum are going to be the same. That change in momentum slows me down and starts moving me the other direction, doesn't it?
Yes.
For him, it just slows him down a little bit. This, by the way, is yet another example of an inelastic collision. So, after we collide, our final momentum must be negative 100, because all the forces here are internal. We're ignoring us pushing against the ground. Right? And you can do that if you get to talk about just before the collision and just after. Follow me? So because then as soon as we start pushing on the ground, then you have external forces. But yeah, how fast do we move? when we collide at the end, our momentum consists of our total masses. We are now combined into one object.
Wait.
Creepy, I know, but we are from a physics standpoint. And so therefore we're one, so we have one velocity at the end. What would that velocity be? Well, I'm negative 100 equals, what's our combined mass? 300. And I'm looking for that final velocity. It's going to be 0.333 meters per second. It will be negative, correct?
Yes.
Makes sense. So that just means Shaq is going to lumber on slower, but with me attached to it. God forbid Shaq ever get this screencast. The restraining order we're going to send to you in the mail. Don't have to do it. So,
Don't ever collide.
Don't ever be one. I'm still one.
so you were weird though. This takes it to a whole nother level. The author of this textbook decided that Adolf would be a great name to give the guy in this question. I'm picturing some really creepy Barnum and Bailey with Nazis scenario here. Because not only do they use Adolf, look at what they have Adolf and Ed doing. They're hanging from rest by the ceiling. Why? What are his? Oh, but still, what? Adolf would be the circle and Ed would be the square. So, what are they doing? Is this like in their home? Is this? What are they part of the circus?
I mentioned something before you started screencasting. I was trying to ask you the question. I just threw up my hand like this, like 3 times, and I was like, "Oh crap! Wait, what am I doing?" I was like, "Wait."
Adolf.
I was like,
So, this is a good example of a question that's going to involve multiple topics in physics. So, this is Adolf, this is Ed, in the Nazi circus. What is their initial momentum? Before they push off each other.
Yes.
What's their initial momentum? Well, 0. They push off of each other. Now, at this point, I want to consider, just like I mentioned a second ago, this is immediately after they push off, before they really start to rise at all. Because gravity in this case will be an external force to the system if you consider it just the two of them. So right after they push off, Adolf has his mass and his final velocity. If you consider this the initial situation, and this the final. And Ed has his mass and his final velocity.
What do we know about their two momentum?
What do we know about each of their momenta? This one and this one.
They're equal to each other but opposite.
So
They're gonna equal to
they were 0 to begin with, right? So there's 2 things and they have to add up to 0. It means one of them's, they're the same size, just one's positive, one's negative. So their magnitudes of the momenta have to be the same. Does that mean their velocities are the same?
No.
Only if they're identical masses, right? If they're different masses, they're going to have different velocities. But their momenta will be the same. Because all the forces were internal. And in this case, they start with 0. The 2 momenta have to add up to 0. So, because the final momentum is 0, and the final momentum is equal to Adolf's final momentum, combined with Ed's, the conclusion we can bring to this is that that their magnitudes are the same. Or if you want to not use magnitudes, we can say whatever one of them is, the other one's going to be the opposite sign. But they're going to be the same number. And that doesn't mean Adolf has to be negative. Well, in this case, since he's still left. So, how many of these things do I know? I just know the mass, right? I don't know velocities for it. But they give me, interestingly enough, how high Adolf rises. So, where do I go from there? They say that when Adolf swings up, he'll be at a height of whatever, higher than he was. Any idea? I'll give you a hint. We're not going to use momentum at this point. What does this speak to you of? We got some energy going on here, right? We got potential. It goes from kinetic energy at the bottom to potential energy at the top. So this is actually an energy situation. The only force is gravity. So the long way around is that the mechanical energy initial has to equal the mechanical energy final. But you're getting good at this. You're recognizing it at the beginning. He's got all what kind of energy? Down there at the bottom. What's he got? All kinds of kinetic, right? Right after he's moving. And at the end, he stops, right? And so what kind of energy does he have here? He's got potential. So the initial kinetic energy, Adolf. Now I gotta be careful. Initial here and final, we're picking up in the chain of events, right? So the initial for the energy situation is actually the final for the momentum, correct? So keep that in mind. I'm going to use initial here. 1/2 mv initial squared, but even though it says a sub o, it is actually this, correct? Because the momentum concerns before they push and after they push. Energy picks it up from there. It says once they're moving to when they're not moving. Equals mass of Adolf, g, height that he rises. So since they give me the height and I know the mass, although it's going to divide out anyway, I can find that velocity of Adolf. Whether you want to call it a final for the momentum situation, and this is where I like to go part like spot 1, 2, and 3, right? So a better way of saying would be, let's say if their initial, before they pushed, that's situation 1. Right after the push is situation 2. So this would be actually velocity 2 in both cases. Point is, I can find that velocity. Once I find that velocity, I can find Ed's, couldn't I?
Yes.
And then I can go back and work the same thing in reverse to find how high Ed goes. Because once I know his velocity, I know his kinetic energy, divided by the mass, divided by g, and I'll have how high he goes. I would presume, I don't know what their masses are. Who's heavier, Adolf or Ed? Adolf. So I would presume Ed would go higher. Because he would have to have, let's see. His velocity, if he's got more mass, he should have a higher velocity, right?
Yes.
And mass doesn't matter when it comes to this, does it?
No.
So therefore, he should go higher, I would think. I encourage you to